Lois.
If you want, it's your
Very
choice.
pessimistic.
Okay.
No, just tell me.
So today is a fun topic. Chi-squared distributions. We'll see a bit more about why we care about chi-squared distributions when we talk about the method of least squares, in terms of how do you find the best fit to certain theoretical relationships from known observations. Right now what I want to do is I want to just introduce this as another random variable that's worth studying. And then we'll see a little bit about why it's so important, why it occurs so much in statistics. Difficulty is the integration is going to be extremely hard. But there are backdoor approaches, and we do not actually have to integrate. So we're going to constantly use the theory of the normalization constant to avoid integrating. So we say x is a chi-squared distribution with new degrees of freedom if its density is the following. It's equal to 1 over 2 to the new halves, gamma new halves, e to the negative x halves if x is greater than or equal to 0, and 0 otherwise. Okay. So when you look at this, you should have a couple of thoughts immediately coming to mind. What's your first thought? Other than may John Lackey's be well rested for tonight, which of course should be on many of your minds right now. What should you be thinking when you see this?
Is it a density?
Is it a density? And related to that is what nus are fine. So we'll have nu greater than 0, often an integer. If nu is negative, there will be issues. Oh, wait a minute. Something is clearly missing.
The x.
Yeah, I just realized I dropped the x to the new halves minus 1. You know that has to be missing, because otherwise this is an exponential with parameter either 2 or 1/2, depending on how you choose things. And there's no new dependence in the integrand. So something has to be wrong. So it had to have been a mistake. Okay, so why do we need nu to be greater than 0? Well, maybe we can even do a little bit better. We want this to be integrable. As we go off to infinity, e to the negative x halves has such rapid decay, we're fine. The difficulty is as x goes to 0. So how small can we take things? Well, actually, no, we do see that we can't do better than nu is greater than 0. If nu equals 0, we have x to the negative 1 that just diverges when we integrate it. As long as nu is positive, we're fine. And it just has to be, what is the correct normalization constant? And so, having already done the calculations, or actually having seen other people already do the calculations, I'm just writing it here, but we'll check it in a moment. Alright, so let's see how we would prove that that is the correct normalization constant. So if you look at this, which function that we've seen recently should be useful right now? I'm just looking at the normalization constant.
The gamma function?
The gamma function. So let's integrate. So we'll study the integral. So we'll integrate from 0 to infinity of x to the new halves minus 1, e to the negative x halves dx.
You said that if it was like 1 over x, then it would diverge?
Well, if you integrate 1 over x when x is near 0, so if you integrate from 0 to epsilon of, well, let's do it epsilon to 1 of 1 over x dx. This is the natural log of x at 1 in epsilon. This is 0 minus the natural log of epsilon. The natural log of epsilon goes to minus infinity. So this goes to, as epsilon goes to 0, this goes to infinity. The function 1 over x is not integrable near the origin. 1 over square root of x is, if you integrate 1 over square root of x, you get x to the 1/2 over 1/2. So if we tried 1 over x to the 1/2 dx from epsilon to 1, that would be x to the 1/2 over 1/2 at epsilon and 1. This would be 1 over 1/2 minus the square root of epsilon over 1/2. And as epsilon goes to 0, that just goes to 2. So as long as the exponent of x is greater than 0, we're fine. Okay. So does this look like the gamma function? What's the difference between this and the gamma function? So I'll use a different variable. So recall gamma of s is the integral from 0 to infinity of t to the what?
S minus 1.
S minus 1 e to the negative t.
dt.
So when you look at this, what's quite frustrating about the definition of the chi-square distribution? What's the annoyance?
The powers are over.
Yeah, the powers are over 2. Why do we have new halves? Why do we have x halves? So we'll see in a little bit where the chi-square distribution comes from. And because of its definition, this is the more natural way to define it. It just means we have to do a little bit of change of variables. So let's let t equal x halves. So dt is going to be dx over 2, or dx equals 2 dt. And so our integral is the integral from 0 to infinity. Now x is the same as 2t. So we get 2t to the new halves minus 1, e to the negative t, and then dx is 2 dt. Well, if I pull out the 2, I'll have 2 to the new halves minus 1 times 2, that's just 2 to the new halves. So that's 2 to the new halves. And I have the equal from 0 to infinity of t to the new halves minus 1 e to the minus t dt. But by definition, that's just the gamma function where s is equal to new halves. And so this proves that if we do divide this this function by 2 to the new halves, gamma new halves, we do have a probability distribution. Okay. Now that we have this, let's see why this is a natural definition. So what we're going to do now is we'll assume x is normal 0, 1, and we'll let y be x squared. So how many of you have taken a stats class? Okay. How many of you will take a stats class? If your hand hasn't gone up once, think hard. Okay? Frequently what happens is you assume errors are normally distributed. Why? I can think of 2 good reasons. So why in stats do we often assume errors are normally distributed? Yes?
It makes them easier to look at.
Yeah, it makes it a lot easier. It makes the analysis a lot easier to look at. So we assume the errors are normally distributed. Frequently, the errors are a function of a lot of different processes, and the central limit theorem, which we'll get to later in this course, kicks in and actually gives us that the errors are normally distributed. So it's not an unreasonable assumption, but it's also an assumption that leads to an analysis we can do. So let's assume x is normal 0, 1, and y equals x squared. What's the most natural question to ask about y?
Its density.
What's its density? So how would we find the density of y? What method would we use? We know the density of x. So how would we find the density of y? What's the name of this technique? Yes? It's not quite the convolution. Convolution would be adding 2 random variables. And so here we're multiplying the variable by itself. So convolution, we're assuming independence. And here we have dependence. So it's a good thing to try, but it's not convolutions. Yes?
You look at the CDF.
Look at the CDF method. So we want to calculate what's the probability that big Y is less than or equal to little y. This is the probability that x squared is less than or equal to little y. This is the probability that x is less than or equal to square root of y and greater than or equal to negative square root of y. Okay? So one way to do this is to actually evaluate the integral of the normal density from negative root y to root y. If I'm going to do that, what would I need to know? Not the normal density, something very closely related to the normal density.
The integral of the normal
The integral of the normal density, it's cumulative distribution function. We can't integrate in closed form the normal density. Fortunately, we don't need to know this. This is, right, whatever it is, let's call it big F of x at square root of y minus big F of x at square root of a negative square root of y. And this is just the cumulative distribution function of y. So now that we have this, we can get the density by just taking derivatives. And so we get Fy of y is now we take the derivative. So we get the derivative of big X, big F of x at square root of y, and now we have to use the chain rule. Now we take the derivative of square root of y, which is going to be 1 over 2 square roots of y, minus the derivative of big F at negative square root of y times the derivative of negative square root of y. The negatives reinforce, and I get a 1 over 2 square roots of y. Well, the nice thing is the density function of the normal is symmetric. So this value and this value are the same. So I can just take this value and double, and that gets rid of the 2. So I get the density at square root of y times 1 over square root of y. Alright, so now all we have to do is remember, what is the density of the standard normal? It's 1 over square root of 2 pi e to the negative x squared over 2. Well, what's my x? So I get y over 2, and now I have y to the negative 1/2. And I'm going to write y to the negative 1/2 as 1/2 minus 1. Is this a valid way of writing y to the minus 1/2? Yes, the reason I'm writing it as this way is because I'm trying to get it to be a chi-squared distribution with new degrees of freedom. I want to write it as nu halves minus 1. And so in fact, this looks a lot like the distribution of a chi-squared random variable with 1 degree of freedom. What's the only thing we have to be careful about? What do we have to check? Yes?
The normalization constant?
Technically, we have to check the normalization constant. I would like to assert we don't have to and that it has to work. This has the same functional dependence on y as a chi-squared distribution with 1 degree of freedom. We know it's a probability distribution. It has to integrate to 1. Therefore, this has to be the same as the normalization constant for the chi-squared with 1 degree of freedom. This is a really subtle point, but it's extremely important. It allows you to avoid doing a lot of integrals. It has the same y dependence, and it integrates to 1. So the only way that can happen is if this is the same normalization constant as a chi-squared with 1 degree of freedom. Now, of course, we can check. We need 2 to the 1/2 gamma of 1/2 in the denominator. Well, note gamma of 1/2 is the square root of pi. And that's exactly what we need. So it all works out. We do get the right answer. There is no need to do the integration. Okay. I think I'm going to leave the definition of the chi-squared on the board just so we can keep seeing that, and I'll just keep using the board over here today. It's not because I'm lazy and I don't want to keep moving the camera. It's I really want to just keep the definition of chi-squared on the board. Okay. So we can begin to see why we care about a chi-squared distribution. It's the square of a normal random variable. And so if you think your errors are normally distributed, squaring the errors is a really good thing. What else could you do to errors if you wanted to add them? So why is squaring errors good? Yes?
You could take the absolute value.
You could take absolute values. Why don't you want to just add the errors as they come?
For the just sum to 0.
They could sum to 0, or they could have cancellation. And so I don't want my errors to be canceling with each other. I want to take the magnitude. And so one good way to do it is I could square errors. Another way is to take absolute values. And we'll talk later in the semester about the merits of the two approaches. So typically you might have some process and you'll have lots of different observations. Each observation will be the square of the normal, hopefully, for the error. And you'll want to add them all up and you want to have an idea of what can I say about the sum of the errors. And if the sum of the errors is pretty small, is your theory doing a good job? Yeah. If the sum of your errors is large, what can you say about your theory? You can use stronger language than that. So if the sum of the errors is large, your theory is not doing a good job predicting. If the sum of the errors is small, you are doing a good job predicting. Well, what's small, what's large? And this is where the chi-square distribution comes into play. Is if our errors are normally distributed, then what we can do is we can say, with this high of a probability, the sum of the squares of the errors will be at most this much. And so if we see something much larger than that, we can even quantify how likely that is and get a sense of how confident we are about our theory being accurate. So it turns out we want to study sums of chi-square random variables. So it turns out the most useful case, or the case we study the most, is sums with integer numbers, with integer degrees of freedoms. So let's say x1, xn have 1 degree of freedom and they're independent. Theorem. x1 plus xn is chi-squared with n degrees of freedom. Two related theorems, let's say xm, xn are chi-squared, well, let's do nu1 and nu2, are chi-squared with nu1, nu2 degrees of freedom and independent. Then x nu1 plus x nu2 is chi-squared with nu1 plus nu2. I claim this first theorem is actually just a special case of the second theorem. So why is the first a special case of the second? And we've seen this technique a couple of times. Okay. But this only says something about sums of 2. So how can I get the n from knowing 2? Sorry?
Just, yeah, but just have like, just use associativity, have sort of x1 plus all the rest.
Good, keep using parentheses. So first follows from second by parentheses or grouping. x1 plus x2 plus x3, for instance. So if we can prove the second one, we can prove the first one. If we only care about chi-squared random variables with integer degrees of freedom, we only have to prove the second theorem in the case that the degrees of freedom nu1 and nu2 are integers. Okay? It is possible to prove it in greater generality. You look a little puzzled.
No.
Okay.
Thank you.
So, if I can prove this for arbitrary nu1, nu2, we're done. Question?
For the first one,
Yes.
Why is it n instead of like the sum from 1 to n?
Over here?
Yeah, do each of the...
Each one of them has 1 degree of freedom.
Oh, okay.
So if each one has 1 degree of freedom, then the sum of them is just chi-squared with n degrees of freedom. So if I can prove this for arbitrary nu1, nu2, I'm done. If I can prove it just when u1 and u2 are integers, then I can still get my first theorem. And the first theorem is really the most important one. It's the one we use the most. Okay. What I want to do is I want to give two different proofs of theorem 1. So first I'm going to prove theorem 1 directly. Okay? And then after proving theorem 1 directly, I'll prove theorem 2. And then once we have theorem 2, we of course have theorem 1 by just using parentheses. Okay. So I've mentioned to a couple of you, change of variables of a 2013 dimensional sphere. How many of you have looked up the change of variable coordinates for a 2013 dimensional sphere? This is a big moment. Why didn't anybody want to look that up? I strongly urge you to look it up to just see how bad it can be. Okay? We're going to avoid all of that, and I think as a nice benefit, we'll actually also be able to get the surface area of the 2013 dimensional sphere as well as its volume. I think that's all going to pop out of what we do. Okay, proof of theorem 1. So, chi1, chi n, I d v chi squared 1, then chi1 plus chi n is, I'm sorry, x1 plus plus xn is chi squared n. So I don't think we've used the phrase IIDRV yet in this class. So IIDRV is independent, identically distributed random variables. Okay? It saves a lot of chalk. Okay? Sometimes people just say IID, where it's assumed that you're talking about random variables. Independent, identically distributed what? Yes, spinach leaves? No. We're talking about random variables in this class. Random variables is understood. People are sometimes lazy and just do IID. So I kind of compromise between saving chalk and I put the RV at the end to just remind ourselves we are talking about random variables. Can somebody give me a way to calculate the sum? I can think of two good approaches.
Convolution.
Convolution is one. Convolution is made for summing independent random variables. What's the other approach?
Linear new expectation.
That would give me the mean, or the moments. And this is a very interesting problem. I believe it's called the hamburger problem. If you know the moments, do you know the distribution? So what else could we do? We have convolution. There's another method we have for calculating densities. We've used it today. The CDF method. So let's do the CDF. The probability that x1 plus xn is less than or equal to x is what? I claim this is the same as the probability y1 squared plus yn squared is less than or equal to x, where yi is normal 0, 1, and xi is yi squared. Why is this the case? Well, we just proved that a chi-squared random variable is just the square of a normal random variable. So if I want to understand this sum, that's the same as understanding the sum of y1 squared plus yn squared is less than or equal to x. What kind of object is y1 squared plus yn squared less than or equal to x? Does anybody recognize what object that is?
An event.
It's an event, but there's a nice geometric interpretation for this event. So we're studying. I'm sorry? It says. I'm sorry? Who is it? It's an dimensional set. So we're studying, I'll write it this way, y1 squared plus yn squared is less than or equal to square root of x squared. Right? It's an n-dimensional sphere of radius square root of x. Now you can begin to see why I'm talking about the change of variable formula for the 2013 dimensional sphere. So what we want to do is the probability is equal to the integral over y1 squared plus yn squared less than or equal to x. Now we have the density function. Well, since these are independent normals, the joint density function is the product of the density functions. So I'll write it very slowly. So we have the joint density function f y1, yn, y1, yn, dy1, dyn. This is going to be the probability that the tuple y1 through yn is at most, when I look at the sum of the squares, is at most x. Because they're independent, this is the same as the integral y1 squared plus yn squared less than or equal to x. 1 over square root of 2 pi, and how many times will I have square root of 2 pi? N times. And then I have e to the negative y1 squared over 2, y2 squared over 2. So I can write this as negative y1 squared plus da, 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 plus yn squared all over 2 dy1 dyn. Okay, so now I basically have a spherical integral to do in 2013 or however large n is dimensions. How many of you remember the three-dimensional changing integral? I can rederive it, but because I've been trained by mathematicians and physicists, I always have a tendency to mix and match. So I would much rather not have to calculate exactly. When you look at this integral, there's something very nice about the integration. What's nice about the integration? What's nice about the integrand? What kind of symmetry do you observe? If you don't observe this symmetry, we have to change variables. We don't want to change variables. We have to observe a symmetry. What's nice about this integration?
About 0.
What about 0?
Well, it's symmetric.
In what sense?
Like, it's going to be the same because all the terms are square.
So it only depends on what? You're close. The magnitude. So you give me the point y1 through yn, and the integrand only depends weakly on y1 through yn. All that matters is how far are you from the origin. So when we change variables, all that's going to matter is how far we are from the origin. So we have to figure out what the spherical change of variables is. And I claim it looks something like the following. dy1 through dyn is going to be dr r d theta 1 r d theta 2 r d theta n minus 1. In the n-dimensional sphere, we have n minus 1 angles. And again, angles are not going to give you a length. To get a length, we have to multiply by the radius. So the volume element is going to look like this. Not quite. There's something else. Times what? Some function of the angles. Right? We saw in polar coordinates it was really nice. It was just r dr d theta. In spherical coordinates, however, you have the sine of theta or the sine of phi, depending on whether or not you're a mathematician or a physicist. So this function g could be quite involved. Okay? And then we're going to have bounds for the angles and all that stuff. And so what we get is we get the integral, let's see, r goes from 0, and what's the radius of the sphere that we're looking at? Square root of x. Then theta 1 goes from alpha 1 to beta 1. theta n minus 1 goes from alpha n minus 1 to beta n minus 1. I don't care what they are. 1 over 2 pi to the n halves e to the negative r squared over 2 times r to the n minus 1 times g theta 1 theta n minus 1 dr d theta 1 d theta n. Okay? Now typically if you're going to do an integral, things that would be nice to know are, I don't know, bounds of integration, that could be useful. The function you're integrating, you know, again, these are all things that typically you would like to have you given an integral to do. We don't have the bounds of integration. We don't have the function we're integrating. We don't know what g is. The important thing to note is there's no r dependence in the theta integration. I get some constant independent of theta because I've integrated out all the thetas. Independent of r. There's no r in it. What is the only thing the constant could depend on? What's the only thing the constant could depend on?
The region of integration.
But we're gonna integrate that out. But there is still one parameter that's alive and kicking that this integral, when we integrate out all the angles, can depend on. N. Right? So I get some constant that depends on n. So it equals some constant that depends on n, and I'm going to absorb the 1 over 2 pi to the n halves into that constant. So I'm getting some constant. I now have the integral from 0 to square root of x of e to the negative r squared over 2 r to the n minus 1 dr. This is the cumulative distribution function. How do I find the density? I take the derivative. So sometimes it's a little tricky. I've got a square root of x as my bound of integration. If I let little f of x, I'll let f of t be e to the negative t squared over 2 t to the n minus 1, big F of t is such that its derivative is little f. So we've just shown that the CDF of x1 plus xn at x is equal to Cn times big F evaluated at square root of x. So once we have the CDF, how do we get the density? How do we get the density from the CDF? Take the derivative. Do we need to know what is the integral of this function? No. Could we integrate this function? I'm guardedly optimistic. N is an integer. I should be able to use what technique?
Substitution.
Yeah, those are the only two techniques we have in this class. Integration by parts, I think, will work here. I want to keep one of the r's to go with e to the minus r squared over 2. Oh, but wait a minute, what happens if n equals 1? Oh, if n equals 1, I would have to integrate e to the minus r squared over 2. My optimism has crashed, right? If n is odd, I'm in trouble. But maybe if n is even, I can do it. Fortunately, we don't need to do it. So now we get the density of x1 plus xn is some constant times the derivative, so it's going to be little f at square root of x, times the derivative of square root of x. Well, that's 1 over 2 root x. So we get Cn, f of square root of x will get an e to the negative x over 2. Now we have x, we put in square roots, we get n minus 1 over 2 And now we have a 1/2 x to the minus 1/2. This is where I wish the blackboard was just a little bit bigger. So what we'll do is we'll put the 1/2 in with the Cn, and we get Cn divided by 2, x, n minus 1 over 2 minus 1/2 is x to the n halves minus 1. This is right, this is nice. E to the negative x halves. Whose density is this? I squared with n degrees of freedom. That finishes the calculation. So what can we deduce about Cn? Therefore Cn has to be, this has to equal 1 over 2 to the new halves, gamma to the new halves with nu equals n. So it should be 2 over 2 to the n halves, gamma n halves. And again, because we know it integrates to 1, and it has the same x dependence as a chi-squared with n degrees of freedom, the only possibility is this. If you think about it, we've just calculated something implicit in this. What have we calculated? When we found Cn, what did we find? We found a really nice geometric quantity. What geometric quantity did we just compute?
Volume.
Not the volume. One lower. The surface area of the n-dimensional sphere. So one way of looking at the measure in n-dimensional on the n-dimensional sphere is we have the surface area, which is constant, and then we're integrating out and letting the radius grow. So you can actually deduce now the surface area of the n-dimensional sphere because of the chi-squared random variable. Right? That's a really nice backdoor proof of what the surface area is. And with a little bit of work, you can get the volume of the n-dimensional sphere as well. Just instead of integrating the function e to the negative, y1 squared plus blah, 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 plus integrate what function? We should replace that function with what if we wanted the volume? I'm sorry?
Do you take everything in the third?
No, so when we integrated e to the minus y1 squared plus yn squared over 2, and we had a 1 over 2 pi to the n halves, this was to get the density. If I wanted the volume of the sphere, all I would do is replace this with what number? I'd integrate over the same region. What function do you integrate over a region to get the volume? You'll kick yourself. One. Right? If I integrate the function 1 over a region, I get its volume. So rather than integrating this function, all I have to do is integrate the function 1 over the region. So you would just go through the calculation and, oh, okay, this is replaced with 1. Oh, okay. So without too much work now, if you want to calculate the volume of the n-dimensional sphere, you've got it. You can actually see how does the volume of the n-dimensional sphere compare to the volume of the hypercube, which has sides of length 2. You can now do that calculation if you want. Okay. So this was the first approach. And so this handles the case when we have sums where each sum is independent of the others and they all have 1 degree of freedom. So now what do we want to study? We want to study now nu1 and nu2. So theorem. Chi nu1 plus chi nu2 is chi squared nu1 plus nu2. So I'm going to assume if I have two random variables, chi squared nu1, chi squared nu2, their sum is chi squared nu1 plus nu2. Why am I not going to use the CDF method? I can't use the CDF method now because if nu1 and nu2 aren't integers, I don't have a really good way of writing things down. Because the chi squared is the square of a normal random variable, do you begin to see why they're calling it chi squared distribution? It's very natural to convert studying integrals for chi-squareds to integrals of associated normals, because they come from squaring. Well, if it doesn't have 1 degree of freedom, I'm out of luck. So I'm going to go back to the CDF method. And this is why I've been desperately leaving this on board the whole time. So the density function of x nu 1 plus x nu 2 is the integral from 0 to infinity 1 over, I'm gonna let C nu 1 be the normalization constant of my first chi-squared random variable to save some time. So then I'll have that e to the negative t halves t to the nu 1 over 2 minus 1. We've got to be a little careful. Times c to the nu 2 e to the negative x minus t over 2. And then we get x minus t to the nu halves minus nu 2 halves minus 1 dt. So we've got to be very careful about this. So there's a small mistake I may have made. What do I have to be careful about? This is the most common mistake people make in using the convolution approach. I have done something wrong. I mean, this is the density of the first, this is the density of the second. I evaluate the first at t, I evaluate the second at x minus t. I don't understand. Where's the mistake?
Bounds of integration.
Bounds of integration, excellent. This is the most often made mistake. This is the density only if t is between 0 and infinity. This is the density only if x minus t is between 0 and infinity. Well, I'm not an idiot. Well, hopefully you'll accept that as a reasonable axiom. I am not an idiot. I would never try to calculate the density when x is not between 0 and infinity. I'm not going to put in a negative value of x. I'm not going to do that. So this part is always fine for t, but once t exceeds x, this is no longer what goes in here. What goes in here once t is greater than x? This expression should be replaced by not t minus x. What's the density of a chi-squared random variable at a negative argument? 0. So I shouldn't have this if t is greater than x. I should have 0. Okay, well, I can integrate the function 0 without too much trouble. So the correction is I don't integrate all the way up to infinity. What's the largest value of t I need to care about? X. Okay, and again, c nu is 1 over 2 to the nu halves gamma of nu halves. Alright, this looks like a fun integral. We can pull out a c nu 1, c nu 2. I have an e to the negative t halves, an e to the negative x halves, and an e to the positive t halves. Ooh! The exponentials are really nice, right? The t's cancel, and I can pull out an e to the negative x halves because I'm not integrating with respect to x. And now I'm left with the integral from 0 to x of t to the nu halves, nu 1 halves minus 1. X minus t to the nu 2 halves minus 1 dt. How many people like this integral? So do you remember any tricks from Calc 2 to handle an integration like this? And remember, nu 1 and nu 2 can be nasty. But let's stop and think. Do we need to evaluate this integral exactly? I only need to sniff out something. What do I need to sniff out? This is the key step. There's only one thing I care about in terms of this integral. What do I care about? I'm trying to get the density function. Where am I evaluating the density function? At x. I only care about the x dependence on this integral. whatever constant there is, by the theory of normalization constants, I can then nail down. So I want to just understand the x dependence. So I want to somehow pull out x from this integral. I'd love to pull x outside of here. What's stopping me? Why can't I just pull out an x and just call it 1 minus t? If instead of t, what would be really nice to have here? xt. So let's change variables. Let's let t equal x times u. So dt is going to be x du. And now t runs from 0 to x. What does u run from? What does u run from now? If t goes from 0 to x, u goes from 0 to 1. Ah, the bound of integration no longer depends on x. Life is really good. And so we get c nu 1, c nu 2, e to the negative x halves, integral from 0 to 1. Now the t over here, t is the same as x times u. So I'm going to get an x to the new 1 over 2 minus 1, u to the new 1 over 2 minus 1. Over here, I get x minus x times u. I pull out an x, I get x to the new 2 over 2 minus 1, 1 minus u, new 2 over 2 minus 1, and then dt becomes x du. Okay? Everybody comfortable on this step? We're going to have just enough time for the miracle to happen. Right? What do we get? C nu 1, C nu 2, e to the negative x halves, x to the new 1 over 2 minus 1, x to the new 2 over 2 minus 1, and then an x. Negative 1 plus 1 is minus 1. So I get x to the new 1 plus new 2 over 2 minus 1 times the integral from 0 to 1 of u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. Does this integral have any x dependence? No, it's a constant. So I can call that some number. Let's call it big C of nu 1 comma nu 2. And I get big C nu 1 nu 2, little c nu 1, little c nu 2 times x to the nu 1 over nu 1 plus nu 2 over 2 e to the negative x halves. I know what c nu 1 is. I know what c nu 2 is. If I really had to, I might be able to evaluate this integral for some choices of nu 1 and nu 2, but in general it is very hard. Do we need to do that? No! This is the exciting part. Right, if you're only going to be awake for 1 minute of class, this is the minute you should be awake. Because after that, you leave. We see that this has the same functional dependence as a chi-squared random variable with nu 1 plus nu 2 degrees of freedom. Therefore, this constant has to be its normalization constant. So done by theory of normalization constants. Okay? So we just made it. You know, it's time to end right now. So we've seen miraculous ways of avoiding integration today. Okay? The theory of normalization constant is incredibly powerful. The CDF method is also very powerful if you can use it. And the trick with the chi-squared random variable is it's the square of a normal. There's a nice geometric interpretation to what we're doing. Okay, so this finishes up, I think, our tour of the standard random variables now. Later in the semester, we'll talk a bit about applications of some of these. And then for Friday's class, we'll start doing some of the limit theorems. I think it's chapters 17 and 18. But I'll send a note about it. Okay.